Hello, my name is Irina Filitovich, and in this demo I'm going to demonstrate my big data case study in healthcare. Let's look at some background for my project. Early stages of drug development involved monitoring of cell behavior and their movement under various tested treatments. For example, someone could be looking for a treatment that kills cancer cells, but at the same time does not kill the healthy cells. The data I'm using has been produced by cell position and shape tracking software. It can also determine when a cell divides into two. The cells are observed in a dish, and the pictures are taken every 15 minutes over several days. Here are some of them. You can see how the positions of the cell changes and how they divide. For example, here the cell is about to divide. Here are the initial and the final states of the dish. Each image is converted into a matrix stored as a CSV file, one per time point, whose elements correspond to pixels. Here's as an example of such matrix. If a pixel does not belong to a cell in the image, it is background and the value is 0. If it does, the value is a positive integer. Here you can see that the outline and the position of cell number 1556. The positive integer indicates the cell's unique ID. Another file is a CSV file with two columns that represent the information about cell division. The first column contains IDs of parent cells that divided into two, and the second column contains the IDs of child cells. So how do we approach the task of visualizing cell movement? We can definitely line up all the images and make a video like this one, but this format does not allow us to look at the shape of the trajectory over time and compare trajectories of neighboring cells. Both articles propose to visualize the cell trajectories over time as so-called XYT plots, or genealogic trees, and they provide examples. X and Y coordinate indicate the position of a cell in the dish, and T represents time. For every cell, there appears a tree-like structure that shows everything that happened with the cell. Where the trajectory splits into two, the cell goes through a process called mitosis, or cell division. Where the trajectory ends, the cell either dies, the process is called apoptosis, or goes outside of the pictured range. The scope of this project is to compare and evaluate different big data visualization libraries that support 3D plotting and have a Python API with respect to the task of cell movement trajectory visualization as XYT plots. I'm going to use Canopy, which is a Python package distribution designed specifically for scientific computing and visualization, and it includes all three libraries I'm going to consider. The libraries are matplotlib, because it's the most popular Python plotting library. It has some 3D plotting and animation support. However, it does not provide much interactive functionality and is not designed specifically to handle large datasets. Despite the disadvantages, I expect the plotting features of this library to be easiest to configure. Plotly is another popular graphing library with Python API, appropriate for large datasets that makes interactive graphs online, including 3D plotting, and this library I expect to give the most flexibility and a variety of interactive controls. And finally, Mayavi is a library specifically designed for interactive scientific data visualization and 3D plotting in Python. It can handle large data sets. Probably this library will be the trickiest to configure, but I'm sure it will handle the big data set best of all. In my report, I have detailed steps that will lead you through the configuration steps necessary and tell you what commands to run. Here, I just outline the configuration steps necessary. First, you will need to install Canopy, which supports various operation systems, and I'm using Windows 7 64-bit. For Plotly, you will also need to register an account and get your own username and API key to configure a credential file to be able to publish your plots online. For Mayavi, you will just need to enable its use in Jupyter notebooks. To run the demo, in Canopy command prompt, navigate to the unzipped folder with my submission and run this notebook. I encourage to run the notebook on the small dataset first, and it is configured that way, no changes are required for that, and then if desired to run on the full dataset, uncommenting some lines as marked in the code. but it will take a long time. So let's load some libraries for data pre-processing and define some functions. The generate colors function generates a random color for each of cell unique IDs in the form of a hexadecimal string. GetCells function takes in a matrix corresponding to one time point and extracts all unique cell IDs present in the data corresponding to this one time point. CellCentroid function was a result of one of the first challenges that I faced, and it was to reduce groups of pixels representing one cell to one representative pixel, or the cell centroid, probably one of these, in order to make plotting easier. Otherwise, there would be too many points to plot and any library would fail. Fortunately, the SciPy package offers a function just like that. This function calculates the center of mass of a matrix. So in order to find the centroid of a certain cell, all I had to do is to knock off the remaining cells from the matrix corresponding to one time point, meaning set their values to 0. This function returns the coordinates of the centroid pixel for a given cell in a given matrix corresponding to one time point. And the CellCentroids function finally returns a dictionary of centroid coordinates where keys are cells' unique IDs. And one more function is to convert the hexadecimal color code strings into tuples of 3 floats, values between 0 and 1, because my AVI library requests color to be in that format. Now I'm going to load the CSV file, which contains the information about cell division. These are the parent cell IDs, these are the children cell IDs, and I'm going to load all matrices corresponding to all time points in one large NumPy array. Then for every time point, I extract cells and calculate their centroids for future use in plotting. Let's find all unique cells present in the dataset. There are 47 in the small dataset. Then move on to the next step. So another challenge that I faced was that each tree should have its own color. But the tree consists of multiple cells and of multiple cell trajectories, because when a cell divides, the two child cells get their own IDs. And the information about the parent cell can only be restored from that CSV file that we loaded into the parents variable. To achieve this, first I generate random colors for all unique cell IDs present in the dataset, and then I iterate through the cells and time points. I'm checking if the cell I'm looking at right now has a parent. If it does, then I update the color of the child cell to match the color of the parent cell. In the same loop, I also gather the coordinates for the trajectories for every cell over time. The trajectories are stored as 3 dictionaries XYZ corresponding to the 3 coordinates, where unique cell IDs are the keys and the values are lists of coordinates showing how a cell moved in space-time. If a cell had a parent, then its trajectory is going to start with the last position of its parent. Now let's get to plotting. First, we are going to plot with matplotlib, and we're going to load some libraries for that. This first plot is actually more of an experiment, which shows how interactive ion function can use that allows continuous plot updates inside of a loop. And this plot can show how the trees grow, and the plot will be rendered in a separate window. I discourage you to run this on the large dataset, as it takes more than 2 hours to render, but I did that and I'm going to show you what I got. This video 100 times faster than the actual rendering was, so you can see how long it takes. This plot is not exactly useful for the analysis of the trajectories, as you cannot zoom in and there are no other interactive features. But it's a nice presentation of animation and plot updating functionality in matplotlib. The next plot is also a matplotlib plot, and it can handle the big data set pretty well, which was a discovery for me. However, it still lacks the interactivity and therefore is not that useful for the analysis of the trajectories, but it can serve for presentational purposes really well. Here what I got when I rendered it for the large data set. The next plot will be a plotly plot, so let's load some libraries to do that. This plot is built from the trajectories that we pre-generated in advance, so it renders pretty fast. It's going to render in a next tab in the browser because it renders the plot online. The plot rendered really nicely, and you can see that there are a lot of interactivity features that Plotly provides. We can zoom in and zoom out, and we can move the plot around. We can switch to the shifting feature, horizontal movement feature, to access some other parts of the plot. And what I like the most is that when you hover over the knot of the trajectory, you can actually see the cell number it represents. So at this point, the cell divided into two, and we can see the parent cell ID and what are the new cells that it divided into. I find this very helpful. And if you accidentally turn the plot over and it becomes confusing, you can always put it back to the original presentation. The cell numbers are marked here in the legend, and the colors corresponding to them as well. And here's what I got when I ran it on the large dataset. I was only able to render it for 1000 unique cells, as opposed to 4690. So I was only able to plot a quarter of my big data set with Plotly. Let's move on to our final library, and that's MyAvi. I'm going to load some libraries to plot with it. And MyAvi plot is also configured from the trajectories that we pre-calculated in advance. And since I'm using the small data set, I'm going to keep this command right here that makes the plot render within the notebook, but with the large data set it's not going to work because the web page will run out of memory and crash. So this message here says that you should comment this line if you want to run it on the full data set. Also here the command would change. This command just calling the plot will render it in the notebook, while mlab.show command will render it in a separate MyAvi scene UI window. So let's see what we have here. Very nice representation of trajectories. I can move the plot around, I can zoom in and out. Colors are very nice, and I like how the trajectories have volume, makes them smoother, helps you see the trajectory because it's thicker. I can easily move the plot around. It definitely lacks all the marks that Plotly shows me, like the cell number and the values of X and Y, but as opposed to Plotly, it was able to render the full data set, which I'm going to show in a moment. There is no lag in the movements that I'm doing. That's really great for playing with the visualization and looking into the data. So let's see what it looks like on the large data set. The conclusion I was able to make is that all three libraries are easy to work with and easy to configure. They all can take in the series of XYZ coordinates as Python lists, which is very convenient. Matplotlib was able to handle the full data set, and that was a discovery. But, however, it does not provide any interactivity as expected, but it is required for the analysis of the visualization. So, probably Matplotlib is only good for presentational purposes. Plotly could only handle 1000 unique cells out of 4690, so about a quarter of the dataset, which I did not expect, but it provides really handy controls for plot manipulation and visualization analysis. The plot stays online for anyone to see, which is also really convenient, and you can share the plots that way. Here are the two links to my two plots, the quarter of the large dataset and the small dataset. And finally, the MyAvi library was able to handle the entire dataset, which is great, and it provides enough interactivity to analyze the visualization. For them, all the movements of the plots happen quickly, there's no lag, and the way they look is great. Thank you so much for your attention. Goodbye.